In 1820, Hans Christian Ørsted placed a simple copper wire over a compass and connected it to a battery. The needle suddenly snapped to the side, revealing a connection no one had seen before. As electrons flow through a wire, they generate an invisible magnetic field that wraps around the conductor in concentric circles. We predict the direction of these forces using the right-hand rule. Point your thumb with the current, and your fingers naturally curl in the direction of the magnetic field lines. Ørsted's discovery united these concepts, proving that electricity and magnetism are two sides of the same physical force. While a straight wire creates a weak field, looping it into a tight coil forces those individual magnetic fields to overlap, concentrating them into a single, much stronger force. Inserting a soft iron core inside that coil aligns the iron's internal magnetic domains. This instantly multiplies the strength of the field to create an electromagnet. We control this strength by manipulating the wire's geometry. Denser coils or a higher current flowing from the battery directly increase the magnetic pull. Soft iron is the ideal core because its magnetism vanishes the moment we cut the power. Hard steel, however, retains that magnetic field, behaving more like a permanent magnet. Industry relies on this instant control. It allows heavy-duty electromagnets to secure massive loads of scrap and release them with absolute precision. By combining wire geometry with specific metallurgy, we turned an invisible field into a reliable, world-moving mechanical tool. Magnetic fields aren't the only outcome of flowing current. Inside the wire, another transformation is taking place as electrons struggle to move through the metal. Electrons glide through low-resistance copper with ease, but encounter a chaotic obstacle course inside high-resistance alloys like nichrome. These constant atomic collisions convert electrical energy into thermal energy. The more electrons crash, the faster atoms vibrate, eventually making the wire hot enough to glow. This process is known as Joule heating. It demonstrates that heat generation is the physical consequence of electrical friction. Controlled resistance provides the exact mechanism we need to generate heat on demand. We deliberately engineer high-resistance nichrome wires into tools that trap and extract this heat exactly where it's required. This vintage toaster is a perfect example. It uses the electrical resistance of nichrome to convert current into the thermal energy needed to brown bread. The same principle scales up to massive industrial electric furnaces, which generate blinding white heat powerful enough to melt and recycle scrap steel. By mathematically engineering electrical resistance, we dictate exactly how energy transforms from invisible current into physical, world-altering heat. Building these magnetic fields and generating heat requires a constant, forceful push. But where does that initial energy originate? A standard dry cell provides that push. It contains a negative zinc container, a positive carbon rod, and a dense electrolyte paste. Reacting with the zinc, the paste strips away electrons. This charge buildup creates the physical push, sending current into the circuit. This antique voltaic pile, the world's first battery, proved we could generate a steady electricity supply using only the chemical reactions between alternating metal disks. These chemical reactions are the primary engine for the controlled current required to animate portable devices. While single-use cells eventually run dry, modern lithium-ion batteries are designed for thousands of cycles. Recharging uses an external current to drive the internal chemistry backward, restructuring the depleted compounds into their original state so they can store energy once again. However, if these chemical engines push too much current too quickly, the resulting buildup of heat can become catastrophic. We use electric fuses as a critical failsafe. These devices rely on the heating effect to detect when a circuit is carrying dangerous current levels. Inside the fuse, a metal element is engineered to melt and snap during an overload. It physically breaks the path for electricity before the rest of the system can catch fire. Electricity is a shapeshifter. It becomes a magnetic crane, a glowing furnace, or a chemical vault. But it only serves us when we strictly engineer and respect its limits.